All right, so this is the last of my really fun lectures that I enjoy giving. After all of this fun, we will compensate by having my least favorite lecture of the semester, the lecture on the chain rule. And I can't even pretend to be excited about giving it. It's the most technical, worst lecture possible. What class would make the lecture easier? Linear algebra, exactly. But we don't have linear algebra. But that will not stop us. So the goal today is to see applications of calculus, to see how we can use calculus to solve certain real problems, and to see what it's good for. And then to compare different techniques and see what does a better job. So the first is actually something we've already done. So this is section 12.6, Approximations. And the goal is we want to approximate a function where we know things going on at one point. We want to approximate what's happening nearby. So imagine we know the value of a function at the point x, y. Then if we had to guess a value for f of x plus delta x, y plus delta y, what is your best guess? I refuse to give you more information. That's it. What's your best guess? Yes? F of x, y. Perfect. And this is called a zeroth order approximation. If I have it, yeah, you should have gone for it. If I give you no additional information, you don't know if the function's increasing or decreasing as you change x. You don't know if it's increasing or decreasing as you change y. Your best guess is to just say, yeah, it's f of x, y. If you could get more information, what information would you love to have? Partial derivatives, perfect. And so if we knew partial derivatives, you could say then f of x plus delta x, y plus delta y is approximately f of x, y where we were, plus df dx at the point x, y, delta x, plus df dy x, y, delta y. And this is the first order approximation. So we're using a little bit more knowledge now. We know how it changes with x. We know how it changes with y. If I were to cover up the df dy, if I just looked at this, what do those first two terms look like? Please, because this is not pleasant. What does that look like? I'm sorry? Yeah, it looks like the tangent line approximation. So instead of the tangent line, this is the tangent plane. So what we're doing is we're approximating with the tangent plane. And remember, we said the way we define what it means for a function to be differentiable is we say the value when we move minus where we predict from the tangent plane is they're so close to each other that even when we divide, bless you, by the distance we've traveled, it still tends to 0. That the tangent plane is an excellent approximation to where we are. So this leads to the notion of df for the change in f. That's f of x plus delta x, y plus delta y, minus f of x, y. So how much have we changed? And this is approximately df dx x, y, delta x, plus, bless you, df dy x, y, delta y. And there's a very nice compact way of writing this. I can write this as the gradient of f at the point x, y, dotted with the vector delta x, delta y. And recall that gradient of f is grad f is df. All these notations are the same, is df dx1 df dxn. Now over here, I'm doing it with just 2 variables just to save chalk. I could do it with more variables. It's going to be the same. And the idea is, if I want to see how much my function changes when I move a small amount, I take my vector of derivatives, and I take the dot product with the direction I've moved and how much I've moved. So if you think about it, I can understand this as a dot product of two vectors. The first components are coming from my gradient. The second components are coming from how much I've moved. So this is a way to reinterpret what we've done with the tangent plane. We can reinterpret the tangent plane as saying, start off where you were, and then take the gradient, take your change vector, and dot it with the direction you've moved, which also includes the magnitude in which you've moved. And this will tell you how much the function has changed. So we can use this to do a really good job of approximating functions. So I'm going to do an example now. So the example is going to be f of xy is the square root of x squared plus y squared at the point 3.1, 3.9. In real life, you would never use the tangent plane or all of this stuff to approximate this function. What would you do in the 21st century? Yeah, use a computer, use a calculator, use a phone, right? There's no reason you would ever use the tangent plane approximation for this. This is a busy work problem. Why are we doing this busy work problem? We're doing this busy work problem because it's going to allow us to see the techniques in action. It's going to allow us to see how good of a job the tangent plane approximation does. That's what I want you to get out of this. So if I'm going to do this, I need an initial point. What point is 3.1, 3.9 close to, where it might be easy to evaluate the function? 3 and 4, right? So note, f of 3, 4 is the square root of 3 squared plus 4 squared. That's the square root of 25 or 5, right? So the question is, if we move just a little bit from the point 3, 4, how does the function change? All right, well, we need to compute some derivatives. Actually, before here, it's probably worth recording. What's the change in x? That's going to be 3.1 minus 3, or 1/10. And the change in y is going to be 3.9 minus 4 is negative 1/10. So I'm moving a very small distance in x and y. And the question is, how accurate is my approximation going to be? I'm changing x and y by 1/10. If I'm off by 5, it's a horrible approximation. If I'm off by 1 over a trillion, it's an incredibly good approximation. How good of an approximation will we be? We'll see that it's going to be like 1/10 squared. And that in general, the goodness of fit is going to be like delta x squared, delta y squared, plus delta y squared, something of that order of magnitude. All right, so let's calculate partial derivatives. df dx is equal to, take the derivative, so I'm going to get 1/2 x squared plus y squared to the minus 1/2 times 2x, so the 2 and the 1/2 cancel. It's very important when you take the derivatives that you write partial f, with the Greek delta, rather than the English d. The English d means a full derivative. We're not doing a full derivative, we're doing a partial derivative. When we get to the chain rule, this is going to be very important. All right, now we need df dy, a similar calculation, 1/2 x squared plus y squared to the minus 1/2 times 2y, and again the 2 and the 1/2 cancel. So we get df dx at the point 3, 4 is going to be x squared plus y squared, so 3 squared plus 4 squared is 5 squared, negative 1/2 power, that's a 1/5. I put in x equals 3, and I get 3/5. Similarly, df dy at the point 3, 4 is just 4/5. And so now we get that f of 3.1, 3.9 is approximately f of 3, 4 plus df dx at 3, 4 times delta x plus df dy at the point 3, 4 times delta y. All right, so this is equal to 5 plus 3/5 times 1/10 plus 4/5 times negative 1/10. All right, 3/50 minus 4/50 is negative 10/50, right? Wait a minute, I'm doing this right? I'm sorry, it's 3/50 minus 4/50 is negative 1/50, right? Negative 1/50 is the same as negative 2 over 100. So this is 5 minus 2 over 100, or 4.98. Right. I've used this problem for years. I don't care to remember the answer. Going through and actually just evaluating by brute force, you get the actual answer is 4.98197 ... That's pretty good. Just by using the tangent plane, we got 2 digits of accuracy. We're off by basically 2 parts in 1,000. About 2 parts in 1,000. This is the power of the tangent line approximation. We got 2 digits right with very little work. Okay? If we were to go with, instead of 1/10, if we were to go with 1/100th, it would be of size basically 1 over 100 squared, or 1 in 10,000. So it's incredible how accurate this is. This is actually exceptionally accurate because the signs are off and they're going to actually help and cancel out a little bit. And so the error is going to be a little bit better than you might typically expect. But this shows you one of the reasons why we care so much about these tangent lines, these tangent planes approximations. They do a really good job approximating the function. How good of a job do you think this would do at the point 2013, 2014? So f of 2013, 2014 is f of 3, 4 plus. How good of a job do you expect this to do? Horrible, right? You should use the tangent line and the tangent plane close to the point you're expanding about. Okay? So for the rest of the class today, I'm going to ignore that. I'm going to use the tangent line and the tangent plane everywhere, because I really like the tangent line and the tangent plane. So what we've seen here that I'm erasing is in some sense an introduction to Taylor series. The more difficult the mathematical concept, the more times you want to see it. And so we'll revisit Taylor series later in the semester. You can skip the rest of this section, but this is an introduction to Taylor series. The next question would be, if we had more derivatives, what could we say about df? How could we approximate even better if I knew more information about how the function is changing? What we're going to do now is we're going to shift to Newton's method and solving problems. And this is going to be a nice way to introduce ourselves to the notion of what is a sequence. And studying sequences is going to be very important towards the end of the semester. Okay. Finding solutions. I can get anybody's birthday in this class in 10 questions or less. And this is not because I have access to personal data of you through Williams College. I'm actually glad that Williams College has stopped giving me your social security numbers. If there is time, since this is being recorded, I will talk to you about a nice social security number scandal involving some admissions officers at Princeton. But I need a volunteer who will either think of their birthday or a random day in the year. All right. Is it your birthday or a random day?
My birthday.
Your birthday. All right, so I will get your birthday in 10 questions. You have to tell me, however, if I'm right, and if I'm wrong, you have to tell me earlier or later in the year. All right? So a bad way to try to guess your birthday is it January 1st? Is it January 2nd? Is it January 3rd? Is it January 4th? This is the 3-year-old approach, right? What is my best first guess? I'm sorry? June 30th or July 1st, right? I would probably go with July 1st because February has only 28 days, and so I'd probably push it over just a little bit. So we'll go with July 1. Later. One question. What's my next guess? Either October 31st or November 1. I'll go with November 1. Earlier. So now we know it's somewhere between July 1st and November 1st. What do we guess? I think like August 15th? We have all of July. We have all of October. November was the wrong guess. We should have said October. We should have said October 1st. Sorry. Let's pretend we said October 1st. It's wonderful what OIT can do with video editing. So I think it was like somewhere like October 1st. So earlier, okay. So now we guess, I think, August 15th. I think that's halfway in between. So August 15th. So then, like September 8th, roughly. All right, so we'll stop here just so we don't make your birthday public knowledge. But so in 4 questions, we've already narrowed it down to the region between September 8th and October 1st. That's not that bad. So what's going on is 2 to the 10 is 1024, which is almost 1,000, which is 10 cubed. So basically, every time I do 10 iterations of this method, I basically gain 3 digits of accuracy. I decrease my error by a factor of 1 in 1,000. So this method is called divide and conquer. It's one of the most powerful methods we have for finding things. So let's say we want to solve f of x equals 0. And let's say we know initially here's 0, here's 1. Let's say the function is positive here and negative here. If the function is continuous, by the intermediate value theorem, it has to go through the x-axis. You can't start off positive and end negative. If you start off traveling 20 miles per hour and end traveling 60 miles per hour, at some point you must have been traveling 30 miles per hour. So the curve has some shape, maybe something like this. And so our first guess would be the halfway point 1/2. We then see the value of the function is negative there, so there has to be a root between here and here. So now we guess the midpoint, 1/4. And we see it's positive here, it was negative here, so it has to be somewhere in between. So now we guess over here, 3/8, positive here, negative here. And so we keep iterating like this. Every 10 times we iterate divide and conquer, we gain 3 decimal digits. So if we want to get 6 decimal digits, we have to do this 20 times. If we want to get 9 decimal digits, we have to do this 30 times. Right? Not that pleasant, but it's a method that will work, and it will get us the answer, and it will get us as many digits as we want if we have the patience. But it's expensive to get more digits. 3 digits cost 10 iterations. I want to show you now Newton's method, which is a much better way for finding solutions to problems like this. This is the problem that basically converted me from a physicist to a mathematician, when I just saw how powerful and how quickly Newton's method worked. So Newton's method. And so the goal is, given, say, f of x is x squared minus 3, find x such that f of x equals 0. Right? So can someone tell me the root? What x works? I'm sorry? 1.72. Technically, 1.72 is not the root. Radical 3. Radical 3 is the root. I'll put radical 3 over here. And approximately, what's radical 3? Approximately 1.7. 1.7 is definitely right. I remembered 2 digits. Of course, after doing this lecture at 10 o'clock, I remember a few more digits now. Any other roots? Yeah, there's also negative. But I agree with you, we don't even want to consider that. That would be horrible to have that as our root. So I want to try to approximate the x that solves f of x equals 0. So I'm going to have some plot of my function. Okay. And now, can somebody give me, and remember, I'm on a lot of medication, so give me a nice answer. Can somebody give me an approximate guess for the square root of 3? Something that's fun to work with. I don't want to do the 1.732 or whatever, or the 7.2 or 7.1. Somebody give me a nice number. 2, thank you. So let's guess that the square root of 3 is 2. I hope you will agree that this is not an unreasonably good initial guess. Right? So we're going to guess 2. And so what I'm going to do is I come up over here and I evaluate my function at 2. Well, when I evaluate my function at 2, I get f of 2 is 4 minus 3, so I get 1. Since 1 is not 0, I have learned that 2, not surprisingly, is not equal to the square root of 3. But we know a really good approximation to our function is the tangent line. And now I'm going to do what you're not supposed to do. I'm going to say, screw this, let's just use the tangent line everywhere. Is the tangent line a good approximation for the function everywhere? No. But imagine it was. Imagine there was no difference between the function and the tangent line. Okay? If there's no difference between the function and the tangent line, then when the tangent line hits the x-axis, what must we have found? We found radical 3. So this gives us a way to get a next approximation, a next guess for the square root of 3. Just say the approximation is perfect everywhere and see where you hit. So the slope is f prime of 2. And since f of x is x squared minus 3, f prime of x is just 2x. So f prime of 2 is just going to be 4. So slope is 4. So what we can do now is we can write down the tangent line. So we have the point 2, 1. We have the slope is 4. So tangent line is y minus 1 is 4 x minus 2. Or y is equal to 4x minus 8 plus 1 minus 7. All right? How do I find where the tangent line hits the x-axis? You got to wait until we get how good this approximation is to class. I mean, we try to get our classes aligned, but so we'll have you guys clap when we get a really good approximation and see how we do there. Yeah, we're not at the approximation yet. So how do we find where it hits the x-axis? Set y equals 0. Set y equals 0 to find where hit x-axis. Great language. All right. So we get 0 is 4x1 minus 7, or x1 is 7/4, which is 1.75. All right, well, we'll do a better approximation later. 1.75, I guess, was not impressive enough. All right, we'll do better than 1.75. All right, that's not bad though. From an initial guess of 2, we corrected to 1.75 fairly easily. And now what we do to continue is we do what every shampoo advises us to do. I'm sorry?
Rinse thoroughly?
No.
Lather?
Lather, rinse, repeat, right? It's the shampoo method of mathematics, right? Once you've done it once, do it again. And after you've done it twice? Yes, always remember your conditions. Yes, very important to remember your conditions in mathematics. So now we try this again. We have the point 7/4. When we plug in x equals 7/4, we get 7/4 squared minus 3. 7/4 squared is 49/16. So 49/16 minus 48/16 is 1/16. So we see it's a pretty good approximation. I draw the tangent line. And you can see it's really close to square root of 3. And so now we just play this again. So now, at point 7/4, 1/16, the slope, so the slope is just 2x, so the slope is going to be 7/2. So the tangent line is y minus 1/16 equals 7/2 x minus 7/4. Or y equals 7/2 x minus 49/8 plus 1/16. So just multiplied through by the 7/2, added the 1/16 to the other side. So again, how do I find where this hits the x-axis? Sorry?
Y equals 0.
Y equals 0. At y equals 0, hit x-axis. So we get 0 is 7/2 x2 minus, all right, so if I multiply by 2, I'll get 98/16. Damn, we're off by like a minute. 98/16 plus 1 should be 97. So minus 97/16. Or x2 is equal to 2/7 times 97/16. 2 goes into that 8 times. We get 97/56. All right. So if you go to a calculator, and what's nice about this is not a horrible calculation to do. This is just the division of two rational numbers. All right. So now what we want to do is we want to do 97 divided by 56, and we get 1.73214 dot 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 dot. Yeah. All right, so since you're clapping, you must know what the square root of 3 is. So what's the square root of 3? Okay, so somebody have a calculator that can tell me that? I have to look for where the special functions are on this thing, which I haven't quite learned yet. Advanced panel. Okay. Square root. All right, square root of 3 is 1.73205 dot 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 dot. All right? That's not bad. Right? Correct, correct, correct. Off by basically 0.5 versus 14. Off by 0.00009 with 2 iterations. What I love about Newton's method is every time you use it, you double the number of decimal digits of accuracy. Divide and conquer, you have to do 10 times to get 3 digits, 20 times to get 6 digits. I do this twice, and I've already got 3 or 4 digits basically. This technically would round up to 1.7321. So technically I do have 4 digits already. We do this again, we will have at least 8 digits correct. We do it again, we'll have at least 16 digits correct. And I'll show you a little bit later today exactly what those numbers are and exactly how close we are. This is phenomenal as to how well the tangent line works. This idea of replacing a complicated function with a simple one. This is one of the reasons why I want to really highlight this point. This shows you the power of calculus. Now, the question is, why does Newton's method do so much better than divide and conquer? Why is Newton's method basically just destroying divide and conquer? Yes?
Divide and conquer doesn't take into account the shape of the curve.
In what sense? I need a specific word. What does Newton's method use that divide and conquer doesn't? The tangent line, differentiability. So if I have a function that's not differentiable, I can't use Newton's method. But if I have a function that's differentiable, I can use Newton's method. Is it surprising that if you have a method that uses more information, it does a better job? No, that seems quite reasonable. Divide and conquer essentially is the intermediate value theorem. All it uses is continuity. Newton's method uses more than continuity. It uses differentiability. It uses the ability to approximate a complicated function with a simple function. Okay? So we can form a sequence of approximations to square root of 3. X naught is 2, x1, the next one in our sequence is 1.75. I'm sorry, x1, x2 is 1.73214 dot dot dot. And this is an introduction to sequences in series. And we're getting these numbers by looking at where these tangent lines hit. So there are more functions in the world than x squared minus 3. There's lots of other functions. Now, there is a danger. If we were trying to get to the square root of 3, everything seems like it's working out. But what could happen? There's two other things that could happen if we try to apply Newton's method. So one possibility is we go to square root of 3. What else could happen? I'm sorry?
The function could go back up, so like it'll change direction from decreasing to decreasing.
Well, I'm saying I have a sequence. I take some starting value, I apply Newton's method. I could eventually converge to square root of 3. Where else could I converge? I could converge to square root of negative 3. Or, horror of horrors, I might not converge to either root. Okay? Where do you think my initial values will be that lead to converging to square root of 3? If you had to guess. What values of starting seeds will get me to square root of 3?
Greater than rad 3?
Greater than rad 3 definitely should work. Can you extend that any further?
Greater than 0?
Probably greater than 0 should go to square root of 3. What about square root of negative square root of 3? Probably the negatives. And what about 0? Nothing. And in fact, if you try Newton's method with 0, not surprisingly, you stay at 0. You're basically, purposely, you don't know which way to go. Okay? It makes sense that you should stay at 0 there. We'll see in a moment what happens when we look at a more complicated function. But a big issue is, where will you go? Will you converge to the root? Will you converge to the root that you want to converge to?
Why is it bad to approximate to negative root 3?
I mean, who would want to root with negative root 3? I mean, it's a bad root. Well, I mean, if I start somewhere near square root of 3, I'm trying to find the root near here. And so if I have an idea that there's a root somewhere through here, I want my method to go to here if I'm in this region. And I want my method to go to here if I'm in this region. If I actually cared about negative root 3, then of course it wouldn't be bad to go there.
Okay. What would happen if you had multiple positive roots?
So we're going to get to that in a moment, or we're going to get to something similar to that in a moment. What we're going to see is going to lead to what's called fractal geometry and chaos theory. How many of you have seen fractals? All right, so I'm going to show some fun movies, or at least what I consider fun movies, later today on fractal geometry. If you're interested in economics, let me know. I'll try to put up some very interesting reading connecting all of this to economic theory. A lot of times, and this is being recorded, so I've got to be a little careful. No, I don't. A lot of economists do not use the most advanced, correct, appropriate math possible. There are many reasons for this. A lot of times you're used to a certain theory, or certain mathematics is harder. There was a similar thing in quantum mechanics, where a lot of the physicists could not accept new quantum mechanics, and the saying was, you just can't convince these physicists, you just have to wait for them to die. And eventually, they did die, and eventually quantum mechanics took over as basically the preeminent theory. So in economics, when you model things like the stock market, a lot of people do a random walk model, where you flip a coin, if it's head, the stock goes up, if it's tails, the stock goes down. Hopefully the coin is biased towards positive, but it depends on the economy. This is an easy model to work with. It's very well studied. It's called the random walk, but it has a lot of issues in terms of it doesn't always do a good job fitting the real world data. And if you're in economics, at the end of the day, it all comes down to, do you match reality? And so Mandelbrot, the famous mathematician who really kick-started the field of fractal geometry, has a lot of papers, and he's done a lot of work with certain economists on trying to apply these fractal ideas to economics. And so if you're interested in economics, there's some really good stuff to read. So let's consider the function f of x is x cubed minus 1. Okay? So can anybody give me a value of x that's sent to 0 by this function? Value of x that's sent to 0. 1. And actually, if you all remember, it's either called long division or synthetic division. You can divide x cubed minus 1 by x minus 1. You'll get, I think, x squared plus x plus 1. You can then use the quadratic formula and find the other two roots. And I'll assume you'll just do that synthetic division at home, and you'll find the other roots are right here, well, probably closer to here. Minus 1/2 minus square root of 3. That's a bad square root of 3. Minus square root of 3 over 2i. And down here, minus 1/2, I'm sorry, that's a plus, minus root 3 over 2I. Where here, I squared is negative 1. This is the x-axis, and this is like the I times y-axis. So this is a brief introduction to complex numbers. As you continue in math and science, complex numbers become very important. One of the goals of this course is to introduce you to some of these key concepts earlier rather than later in your career. And so this is a very convenient way to write things down. So I have my 3 roots to this function. And so what I'm going to do is I'm going to apply a generalization of Newton's method to find the roots. So maybe I'll have to be a little bit careful because now this is going to involve complex variables. I don't want to go into all the details. I just want you to just tell me, we'll call this root 1. This is the point 1, root 2, root 3. And we'll color it red, white will be patriotic, and blue. So either say a number or a color. If I start over here, what root do you think I go to? Red. If I start over here, if I start over here, if I start over here. So how do you think you tell the difference between when you go to blue and red? Midpoint what? In what sense? Yeah, so all 3 of these are 1 unit from the origin. If I draw this line over here, does it seem reasonable conjecture that everything in this region goes to 1 because it's closer to 1? Everything in this region goes to 3. Everything in this region goes to 2. If that were the case, the world would be a lot simpler than it actually is. And so what we're going to see is we're going to do the following. We're going to play a coloring game. We're going to take any point in the complex plane as our initial seed for Newton's method. And then we're going to apply Newton's method, and we're going to see where do we go. And if we end up at this root, we color the point red. If we end up at this point, we color the point white. If we end up at this point, we color the point blue. And that's the rules of the game. Okay. So what I'm going to do is I'm going to show the movie now. But before I show the movie, just so we can clap again and throw them off and show them that we can be happy too, I want to just show you the numerics for Newton's method. So this is a very simple program in Mathematica. I'm guessing over here that my first guess for the square root of 3 is 2. Okay. Now I'm just doing it a couple of times. So here's the square root of 3. You should memorize this for the final 1.7320508075688 ... All right. So the first guess, the 0th guess, the start was 2.00, not so good. 7/4, 1.75, the difference is 0.017. Our next guess, 97/56, that leads to a difference of 0.00009. And 97/56, this is a great number to work with if you're a computer scientist. It's a ratio of 2 integers with a really small denominator. Let's do Newton's method another time. Well, let's have my computer do it. 18,817 over 10,864. And again, we had stopped over here. We had done it twice. If we had done it one more time, this is what we would get. It's not horrible to get this. The difference is basically 2.4 times 10 to the negative 9. We're essentially getting 8 or 9 digits of accuracy. And we're doing it with a denominator that only has 5 digits. If I write square root of 3 as a denominator with 10 digits, yeah, I can pretty much guarantee I can get 9 digits accuracy. We're using a much smaller denominator. And we're finding these numbers very quickly, and these are rational numbers. They're ratios of integers. This is beautiful for the computer. If you do it one more time, the difference is 10 to the negative 18. You've overflown what your calculator can probably do. I'm still learning how my smartphone works. I don't know if it can do 18 digits accuracy. If you go to 5 terms, I basically can't even tell the difference anymore with the number of digits I gave you for square root of 3. You're already at like 36 digits accuracy with just 5 iterations. So it's incredible how well this works. This is the power of calculus. So again, for many of you, this should be your 3rd calculus class. Calc 1, Calc 2, Calc 3. Why are we spending all of our time on calculus? It's not because we need you to have something to do, right? And we need to be able to hire mathematicians to research number theory, so they need jobs, they need to teach classes. Let's have them teach this thing called calculus. We're doing calculus because it's useful. You can solve problems. You want to find roots to things. You want to find solutions. Newton's method is a very powerful way to search the space. It uses this notion of differentiability. It uses this notion that the tangent line approximation is a really good approximation for the function. It generates a sequence, and we can keep iterating the sequence. And so you can prove that every time you iterate, you double your digits of accuracy. So absolutely amazing how well Newton's method does. All right, so what I'm going to do now is I'm going to shift to the movies. I think this is the movie I want. Yes. All right, so we're doing z cubed minus 1. They're using z rather than x because it's a complex variable. And what they're doing is they're zooming in. So basically, this blue region, okay, so my colors are a little bit off from the computer. Over here, this is where root 1 is, this is where root 2 is, this is where root 3 is. And notice that our guess was pretty close. Our guess was that, if we're closer to root 1, we go to root 1. If we're closer to root 2, we go to root 2, closer to root 3, we go to root 3. But not quite. It's not a perfect boundary cut. There's some very fascinating structure. One of the things that's really interesting is this redness over here. I'm closer to root 1 and root 2, but I end up going to root 3. Over here, these points are closer to root 1, but they go to root 2. The key defining feature of fractals is this incredible self-similarity, that as you zoom in, you keep seeing the same thing again and again and again. And so what I'll do is I'll play the movie for a little bit. It's not that long of a movie. And you see that as you zoom in more and more and more, you keep seeing essentially the same thing. Very restful. But as you keep zooming in, it's the same pattern. Now you notice it's getting a little black and hazy and whatnot, like the guy's conking out. Do you know what's happening? What do you think is going on? Yeah, we're getting into issues with how well can we compute something like this. And so with a lot of stuff like this, you have to keep iterating polynomials. And so in the additional comments, I will talk about a fast way to evaluate polynomials. If there's time at the end of class, I'll quickly show you how to do that. If you don't do something like this, it's not possible to do this in a reasonable amount of time. All right. It is not allowed to talk about fractal geometry without showing something about the Mandelbrot set. This is the most famous of all the fractals. And so the key thing to notice is that as you zoom in again and again and again, you keep seeing copies of what you started with. And this wonderful flowery language to describe all the different shapes in the Mandelbrot set that you see as you zoom in. The other thing is people have to choose some kind of strange music as they're doing in the zoom. And so half the time I think is spent on the mathematics of these pixel evaluations. Half the time is what should the soundtrack be. But you see fascinating shapes. And so the colors determine, for the Mandelbrot set, how quickly something blows up or how quickly something converges to something. And so the question is, as we keep zooming in, will we see the Mandelbrot set again? What do you think? It almost looks like there's something over there, maybe over there. So unfortunately, in something like this, we have no choice but to go where the person who recorded the simulation wants to go. I actually wrote a program to do this in Pascal many, many years ago. And without using fast ways to evaluate polynomials, it took too long to run. And so one of the big things is just because you have an algorithm does not mean the algorithm will run in a reasonable amount of time. You can start to see things that could look. All right, so still zooming in. So the other one was at least nice enough to tell you how far we're zooming in. At this point, there's issues with the resolution. And so unfortunately that clip did not actually go far enough or zoom in well enough to see. So let me just do this one. See, this has the more funky techno. All right. Is there any reason to have this spin?
Why?
But I mean, I think this is fun as you watch as it zooms in. And so we're getting really, really close to that point. And as it keeps zooming in, eventually you should start to see a Mandelbrot set. So what you want to do is start going to one of these places over here, please. Don't keep going to this point over here at the very end. Okay. And so now we're going right down towards the middle. So resolution's not quite good. But for the most part, these colors are correct in terms of what you're seeing. And so there is something right there in the center. It's kind of hard to see, but there it is. There's the Mandelbrot set. You're zoomed in at that incredible level. Now, this is not just a tie-dye shirt, although it would make an excellent tie-dye shirt. I would definitely buy that. But of course, I have a grant that I can expense things on. I've bought Cookie Monster, and oh, that's right, this is being recorded. Hello, auditors. One of the earliest applications of fractal geometry was in the major motion picture industry. If you've seen Star Trek II, The Wrath of Khan, when they do the Genesis torpedo hitting the planet or hitting the moon, that was all done with fractal geometry. So what I want to end with today is you guys are lucky. You get one extra bit of material over 10 o'clock. Is I want to show you how would you evaluate a polynomial quickly. So when you're doing all of this stuff, I mean, this is an incredible amount of computation. How would you evaluate something like this quickly? Oops. And so let me just quickly close this. Okay. I did it log off. It logged off? Okay. So let's take a polynomial. So this is called Horner's algorithm. So let's say I give you f of x is 18x to the fifth minus 11x to the fourth plus 2x cubed plus 3x squared minus 8x plus 8. Not plus 2, plus 8. How many multiplications does it cost me to evaluate 18x to the fifth for a specific value of x? So how many multiplications does it cost to evaluate 18x to the fifth? 6? I think it's 5. It cost me 4 multiplications to get x to the fifth, right? X times x is x squared, times x is x cubed, times x is x to the fourth. X times x is x squared, times x is x cubed, x to the fourth, x to the fifth, times 16 is the 16x to the fifth. So this costs me 5 multiplications. How many multiplications does this cost? 4, right? 4 multiplications, 3 multiplications, 2 multiplications, 1 multiplication, 0 multiplications. All right, addition is cheap. I'm not even going to bother counting how many additions I'm doing. I don't really worry about additions. So what I have here is I have 5 plus 4 plus 3 plus 2 plus 1. All right? So more generally, if I had a polynomial of degree n, I would have n plus n minus 1 plus n minus 2 plus 2 plus 1 plus 0 multiplications. If you haven't seen how to sum this series before, I'm going to show you a very easy way to sum this. If you let S be the sum, well, I could also write things in reverse order. And so when I write them in reverse order, I get 2s. What's n plus 0? N minus 1 plus 1. N minus 2 plus 2. Every term is n, and I have n plus 1 terms. So 2s is n, n plus 1. Therefore, S is equal to n plus 1 over 2. That's how many multiplications we have. That's how expensive it is to evaluate a polynomial. So if n equals 5, then we would have 5 times 6 over 2, or 15 multiplications. I'm going to show you a phenomenal savings. Right? We have the following. 18x minus 11 times x plus 2, the parentheses have to keep getting larger, times x plus 3, parentheses getting larger, minus 8, I'm sorry, there's an x here, minus 8 times x plus 8. I claim that this is the same polynomial. Let's check. The first term is 18x, x squared, x cubed, x to the 4th, 18 fifth, 18x to the 5th. The next term is negative 11x, x squared, x cubed, x to the 4th. So when you distribute everything out, this is the same. But if you look at it, now the number of multiplications, it's 1, 2, 3, 4, 5. 5 multiplications versus 15, or in general, n versus n plus 1 over 2. You're essentially taking the square root of the number of multiplications in the naive way. That's how much faster this is. So this is a huge theme in mathematics and computer science. It's not enough to do something. You want to be able to do something well. You want to be able to do, bless you, to do something efficiently. And so to see those pictures of those zoom-ins, we have to be able to iterate these polynomial maps very rapidly. What I love about this is this is not deep math. The calculus you're learning is much harder than this. But this clever idea is absolutely revolutionary in terms of what we can do. So to just end today's class, we saw the power of approximations. Anytime you have a cell phone or some portable device that's doing computations, it's often using something like this. It evaluates functions at key points, and it has a storage in the memory. It has some data table, some lookup table, and it has a way to interpolate between values. Maybe it uses calculus to approximate between values. Maybe it forms something like a Newton sequence to find values. But these ideas from calculus, they're being used in the devices all around you every day. So I hope you got some sense and appreciation for what calculus can do and how fun it can be to just keep in reserve for Monday's lecture. Okay? Going to be horrible. My least favorite lecture.